small little graph. Like if I was doing this, I wouldn't even make like the tick marks on it. I would just draw an XY graph and do the general shape if I was the one doing it. So the first one I give you is the identity function. The identity function, basically any linear function could be made from transforming the identity function. But it's just, here's the graph, here's the function underneath it. Again, if you want to make 1 through 5 on there, you could, but if it was me, I would just draw it and just make the line that goes through it. It has a y-intercept of 0, it has a slope of 1. The reason it's called the identity function is because whenever you plug in there for x, you get the same value for y. So all the ordered pairs are like 0, 0, 1, 1, 2, 2, -1, -1. And what would the domain of this function be? Yeah, it's all real numbers. Right? There's no asymptotes, there's no holes, there's no imaginary numbers. X can be anything. And what about the range? The same. Most of the functions that you dealt with in Algebra 2, most of them had domain and range of all real numbers, but especially linear functions. And then your book likes to give you an interesting fact. Some of these aren't so interesting. Don't write these down. This is just me trying to, like, I think it's funny that the book tells you this, but this one's not that interesting. They get better. But this says this is the only function that acts on every real number by leaving it alone, which means whatever you plug in, you get back the same thing. That's not very interesting, but there you go, the identity function. Because this is all we're going to get through today are these 10 functions, your homework today is just going to be matching equations with graphs. But it'll be much easier because you'll have the equations that go with them. And then there's some that ask questions like, which of these are odd functions? Which of these are even functions? And so we can kind of say that as we go here. What about this one? Would this be an even or an odd function? I don't know what that means. Even means that it would be the same on both sides, right? Symmetric with the y-axis. Odd means symmetric with the origin. This would be an odd function. So if we say this as we go, it'll make that homework question even easier. Well, I kind of want to hide the interesting facts from here. I don't think I did that. The squaring function, your book calls this the squaring function. I call this a quadratic function. But squaring, they call it squaring because it's x squared. And again, these are what, I don't know what Mr. McClure called these or what the Algebra 2 book calls them, but I call these like the parent functions because if you know what x squared looks like, then you should be able to graph any squared function if you know the transformation, like what it means to move up, down, left, right, reflection, stretch, shrink. So if you know these, then you could graph any quadratic function using those. And so when I give you the domain and range of this is the domain and range of just this function. Obviously, if it was moved around, the domain and range could change. But again, domain is what x can be. So when you're trying to think of your domain, you always want to look at the equation and think, is there anything x can't be? And what's the answer on this? Is x restricted anyway on this graph? No, you can plug anything you want in there, which is why we have a lot of domains of all real numbers. What about the range on this? It starts at 0 and it goes up from 0 to infinity. And on a quadratic, the range will always be restricted because there's always either a low point or a high point if it's going down. Interesting fact, the graph of this function called a parabola has a reflection property that is useful in making flashlights and satellite dishes. So thank you, math, for giving me satellite TV. Oh, you tell me, is it odd or even? Even, because it's reflected over the y-axis. Whatever you plug in here, you get the same thing over here. Makes sense. Cubing function, I call this a cubic function. Maybe I should change what I say, but I can't at this point in my life. But again, it's just because it's x cubed. once a long time ago, who knows how old this kid is now, but he, in Algebra 2, he said, I'm just going to guess all real numbers every time for domain. And that's a pretty good guess. I mean, there are exceptions to that, but it's a pretty good guess that the domain is going to be all real numbers, because most of the time, X isn't restricted. You can plug anything you want in there, which means the domain is all real numbers. What about the range on this one? Also all real numbers. Quadratic, the arrows point in the same direction, so it's not all real numbers. But an odd function, the arrows go in opposite directions, which means this side goes up forever, this side goes down forever. So it's also all real numbers. Interesting fact. Ooh, this is a little calculus fact, probably not as interesting as satellite dishes. But the point where it turns there at the origin is called a point of inflection because it changes curvature at that point. We say this side is concave down and this side is concave up. And if you take calculus, we'll talk a lot more about that. That's not very interesting. Moving on. We've been dealing with this function, only really ugly ones. The book calls this the reciprocal function because the reciprocal of x is 1 over x. I tend to call this a rational function because anytime you have a polynomial on top and on bottom or an x on the bottom, that is a rational function. So again, both of those are acceptable names. I will use them interchangeably. And again, the basic one is 1 over x, which means we have that vertical and horizontal asymptote along the x and the y-axis. And then we can get crazy, like the ones that we did on our homework for yesterday. Now this is where domain and range get a little trickier. In Algebra 2, you don't do this like Chapter 9, so you don't have to deal with these for a while. But what can't x be in this problem? 0. So my domain is everything but 0. And again, I don't care which way you do it. I tend to use interval notation because the book uses interval notation. I feel like most colleges these days use interval notation. And if I'm going to say everything but 0, I have to just skip over 0. So I say negative infinity to 0, parenthesis, union 0 to infinity. But if you just said x such that x cannot equal 0, that's the same thing. That's set notation, that's interval notation. I don't care which one you use as long as you use one of them correctly. If you're doing set notation, make sure you use x when you're talking about domain and y when you're talking about range. So for the range, again, because we've been talking about asymptotes, what can't y be in this one, or what would the horizontal asymptote be of this problem? Also 0, which means my range is exactly the same. I'm not going to do all these in both notations, but I'll do this one in both notations. Okay, rational functions. This is actually called a hyperbola. If you remember doing conics last year in Algebra 2, you did hyperbolas like they were like crazy, not slanted hyperbolas, they're like this or like this. Also useful in satellite dishes. Oh my gosh, thank you, math. See, you all think you don't use math every day. You don't, but someone else did a lot of math for you to have all your awesomeness that you get to use. And if it wasn't for someone teaching them math, then we wouldn't have all that technology. So, okay, moving on. Satellite dishes. So let's move today. Square root function. We've talked about this one also, I believe, this year. Oh, my eraser. Basic square root function. Oh wait, did we need to do even or odd on that one? It is odd. See, like you already know now. It's over the origin. I always say a square root function is half of a parabola on its side. So if you know that shape, then it's easy to recognize when you have a square root function. The domain and range is always going to be restricted on a square root function because you can't have a negative under there. Right, I guess there's exceptions to that, but we're just going to say for the most part it's restricted. And if you have the graph, it's easy to see the domain, but also if you have the function, you can't have a negative under there, which means it's going to be like an inequality domain, right? You can only have numbers that are positive, right? Greater than or equal to 0. So in interval notation, I would say that's starting at 0 to infinity. I guess I'll do this one in set notation for you also. I would say x is greater than or equal So whatever number is the smallest you can plug in there, that becomes the start of your domain. And your range, and when I taught Algebra 2, I always said your range is whatever you get when you plug in that smallest number for x, that's where your y's start also. And in this case, the y's also start at 0, which means 0 to infinity. If it was moved up, then your range would change. If it was the bottom half, it'd go to negative infinity. Oh, here's a fun one. Put any positive number into your calculator and take the square root, and then take the square root again, and then take the square root again, and so on. Eventually, you will always get 1. Now you can stop paying attention and type that in the calculator. Just keep saying square root, square root, square root, square root, square root, square root, square root. No, you don't care, you won't work. And it does work, because when you keep taking a square root, it gets smaller and smaller until you get down to the square root of 1 is 1. And then, there you go. So start with a giant number, and then just keep taking square root, or whatever number you want. Even if you do a decimal, or has to be positive, or imaginary. Oh wait, we need to say that. What about a square root function? Is it even or odd? No, it's only on one side there, so it's neither. I know, we need one that we can just hit square root. I think Ariel has also one that you can just hit the square root button over and over again. Because this one you have to like hit answer and square root and that one, so you hit that square root button. It works. Absolute value function. That is the one graph that you get to make that has sharp corners. All of our other graphs are smooth curves. Absolute value is a V-shaped graph because whatever you plug in here, when you plug the negative numbers, you get the same thing, which means this is a even or odd? Even function. I do want to point out that the book uses the notation ABS for absolute value instead of bars sometimes. That's because on graphing calculators, you can graph absolute value functions, and the notation is ABS, like that's the button that you go and find, unless you're super fancy and I have enough of bars. But just know that means the same thing as absolute value. And to me, this looks very much like a quadratic, which means is the domain and range going to be the same as it was on the quadratic function? Yeah, the only difference is the quadratic is a smooth curve, but it's still an even function on both sides, which means where does my x start? My lowest x value on here. Oh wait, just kidding. Negative could be infinity, right? There is no lowest value. It could be everything. It was a trick question. Every positive number, every negative number. I was actually thinking of range. And the range on this would be 0 to infinity. Again, if they threw other stuff out here, then the range is going to change. But for the basic one, you can't get a negative number when you take an absolute value. That's why it's all positive. Okay? What's the... this is just a math interesting fact. Not that interesting to you if you don't like math. We say that this has a corner, which I think you would agree with because it's a sharp change, and all of our other functions are smooth curves, which is why I tell you not to make jagged edges on your other graphs. Okay? Corners in quotation marks. How many do we have here, kids? We're getting close? 7. Whew. Got a lot to go here. She's a baby, so she seems less threatening, right?
Yeah, she has a stroller and she's just going to try to hear it, but she could just disguise eventually left.
Is she on the sidewalk here?
No, she doesn't know the parking lot. Like,
Was she just walking around?
that truck.
Last year I called and reported that there was a random man walking through our yard with a sign, and it was the guy that was going to mow the yard, and Mr. Puckett made fun of me a lot because I called and reported. There's some guy out walking in the yard holding a sign, and they like went out there, and it was just a guy picking up before he mowed. But I'll let him know that the person with a baby walking. Just be aware.
It could be a bomb.
It could be a bomb and not a baby. We these step functions because there are more than one type of them, but the one that we deal with the most is a greatest integer function. We call the step function because it looks like stair steps, right? In Algebra 2, they didn't give you this notation, right? Again, the book uses this notation because that's the calculator notation, and I think maybe something like this. Do you remember that weird thing? It's kind of like double bracket or like lines and then bracket. Here's the big thing to know about this. The greatest integer function is like its own little definition, its own little function. When you put a number in the greatest integer function, you round down to the next lowest integer. So round down to next lowest integer. Down and lowest are kind of redundant to say there, but people get confused by it because it says greatest integer, but it's the greatest integer less than or equal to that number that you're putting in there. So if you put an integer in, you get an integer out. If you plug in 0, you get 0. You plug in 1, you get 1. You plug in 2, you get 2. But what happens is when you plug in a decimal or a fraction, if I plugged in 2.7 here, what I get back is rounding down to the next integer, and round to the next integer would be 2. Because at 2, it goes up to the next one, right? Megan, I think she needs you. You can go if you need to. I'm probably going to be talking to the bell. We have 5 minutes. We gotta go. So the domain of this, do you agree I can plug anything I want in for x? So the domain is all real numbers. But the range is not all real numbers because there's these big gaps in this, right? What are the only y values I get out of this? Integers. So we can't really write this range in interval notation. We have to say the range is any y value where y is an integer. The fancy way to say that is you say y is an element of the integers. Right? That's super fancy. But you can just say y is an integer. Yes. Oh, step functions, okay. This is 7, this is 8. Oh my gosh, we gotta bring it here. Something hostage. Ready? Go. Exponential function, e to the x. Really, the one that we did in our notes the other day that was like, or the homework that was like 1.5 to the x, that's an exponential function too. E to the x is just that special number, but an exponential function is going to have a horizontal asymptote. This side is going to grow exponentially. We're going to say the domain is all real numbers, but the range is never going to be negative. It's actually never going to be 0. So we're going to say parentheses 0 to infinity. And then they just talk about what E is, but we don't care. We don't talk about any more of that. Go. She's gone already. So guess what? ln is the other one you need to know. Oh, I think this is it. Because 10 is like piecewise, and we're not. Oh no, wait, I forgot. I know what 10 is. ln is the reciprocal of e, which if you think about, not the reciprocal, the inverse of e, and so it's going to have a vertical asymptote, and it's going to slowly go up like this. So the domain of this one is going to be 0 to infinity, and the range is going to be negative infinity to infinity. Chapter 3 is all about e and ln and log, so we'll review all of this again. And again, this one is kind of an interesting fact, that this goes up so slowly that if the, it says if the x and y axis were both scaled with unit lengths of 1 inch, so each one represented 1 inch, you would have to go 2.5 miles along the x-axis to go up 1 foot on the y-axis, because that's how slowly increasing that is. That's kind of cool. The last one, we don't really use the last one in math class that much, but you use it in science, so I like to show it to you because, you know, math and science are best friends. My bad. The logistic function. And it's this ugly thing down here. The big thing is it's easy to recognize because it has two horizontal asymptotes. Nothing else we do in math class has two horizontal asymptotes. But this comes up in population growth, right? What's that called when your population reaches a high point? It can't go anymore due to the environment. The carrying capacity. So when they talk about population growth, it's always in this logistic growth model because of the carrying capacity. And so the domain of this is restricted. No, not restricted. The domain is negative infinity to infinity. But the range is between 0 and 1. Don't leave, okay? I'm holding my stick. I'll write fast. I'll like send an email. Your homework today is, I'm going to cut it off, okay? So you only have to do part of it, which is super great for you, which means tomorrow you have very little homework. And all you're doing is matching graphs up, which means it kind of lets you know if this makes sense or not. Can I go or not?
Yeah, but this
This is all, this is neither.
all my students to the office, please.
No.
Kevin Johnson,
Here we go.
Alexis Stice.
You're going to stop at, oh my gosh, I don't know. I need to have my book open. I think like 24, but let's see. Maybe before that. Oh yeah, which means you should be able to go all the way to 24, and it's all just matching and saying which ones are even, which ones are continuous, which ones are not continuous.